if you look at this is just I'll have to again.
Yeah, good morning.
Join the column.
Yeah, hello. Huh.
Yeah.
So students, can you hear us?
Yes, sir.
Yes, sir.
Okay. So
Yeah.
CRM,
So
what to you?
okay. So what I was saying is that along with this you need true and false uh, to make. So this is a functionally complete set.
The screen is not
So
visible.
these things we saw in the morning.
CRM, can you share your screen?
Oh, sorry. No. Okay. No. What is happening?
Yeah, now it's visible.
Okay. All right. So all right. So these things we saw in the morning. So now let us get into the theorem proper. So the first, so we need to define certain operations. So complementation is an important operation. So we'll see how complementation can be defined using F1, F2 and F3. So just to recollect, what is F1? So can someone tell me what is F1? What does F1, what kind of function is F1? Yeah.
Which does not
Non-truth
belong to
preserving.
true.
Which is, this is important, not
Doesn't
in
belong
true.
to T.
F2 is not in false and F3 is not in, it's not a monotonic function. All right. So let us just see. So now actually the arguments are not so difficult also, but these are interesting arguments. So since F1 is not truth preserving, okay, so you know that, let us just, so since F1 is not truth preserving, we know that, so F1 is not truth preserving, right? F1 is not truth preserving. So what is the requirement of truth preserving? Requirement of truth preserving is that F etc. is T, but F1 is not truth preserving. So this is not true, right? So if it is not true, what can it be? It has to be F, because there are only two values. If it is not true, it must be false. So that is how, okay, by the way, we define F star. So instead of writing all of these, we call this F star. Let us say F star P. F star P is simply equal to, actually this is what you have to do in the lab really. So that means, how do you get F star P? So if you think of, what you have been doing, this making a component. So you have F1, this is F1 star. You have got F1, right? So etc. So this is how you get F1 star from F1. Okay, this is how you get F1 star. Alright, so this is F1 star. So as you can see in the truth table for F1 star, so similarly you have got F2 star also. You have got F2 star as well. So this is, so now you know how you get this F. Because of this, because of this, So from here, what do you see? Here, what you see is F1 star T is equal to F, right? F1 star, this is F1 star. This whole thing. Alright. What about F1 star F? Well, you don't know. You don't know. Alright. So that's how you have, this part. You don't know about this. By similar reasoning, because F2 is not F preserving. So you know that because F2 is not F preserving, so you can say that F2, if you say, so F2, you can say F this must be true, or you can say that this is not equal to false, so it has to be true therefore, right? And this whole thing we say this is F2 star F. So F2 star F is true. So that is what we have here. F2 star F is true. And similarly, we do not know. This is not known. So this table, which is shown here, I hope this is clear to you now. Any questions about this table? Yeah? Is it okay?
Yes, sir.
Yes, sir.
Good. So now we do a bit of case analysis. What you see is, so let us just write down the same table here. Alright, so I'm just copying from there. That's so this much we have fixed up. Now we do a bit of case analysis. So this one can be what? This one can be, you don't know, right? So this one can be either true or false. Similarly, this one can be either true or false. All right. Now, if this is true, then what do you get? Then this becomes an inverter, right? If you take this choice, means F is already there. If you take this is an inverter, or you can say this is an inverter, right? And similarly over here also, if you take this choice, so if any one of these, so if this one is true or if this one is false, then immediately you have an inverter. All right. So you just need to examine the truth table to see what you get. All right. But if it is not so, if this is the case, then you can get an inverter from either this or this. Okay. But if that is not the case, so suppose it is, false instead. All right. Suppose it is false. So this is the other possibility, right? And both of these taken together. So let me just say both of these taken together. Why together? Why am I saying together? Why together? Can you say why I'm considering together? Yeah? Why together? Anyone? See, together for a very simple reason, because if they are not together, then unless this one is false and this one is true, unless that is the case, you already have an inverter. You don't need to do anything more. All right. So if you are going ahead, it means that this is not true and this is not false, because had this been true or had this been false, we would have had the inverter, isn't it? Is that okay? So if we haven't got an inverter as yet, then this one must be false and this one must be true. Do you get it?
Yes,
So
sir.
Yes, sir.
what is so what is this? So in this case, what you have is, what is F1 star P? F1 star P is false. So it is a constant function, and here F2 star P is true. So you have two possibilities. One possibility is that, so let me write it this way. One possibility is at least one of F1 star or F2 star works as an inverter, okay? This is one possibility. And what is the other possibility? Other possibility is it's a constant function. So these are the two possibilities, all right? These are the two possibilities. So either you are, means in this case you are done, and in this case you need to do something more, all right? In this case you are done, but if it doesn't work out this way, then in this case you need to do something more. So let us see how we can proceed. So now you know that, so that is this part, or if you like, I'll show in that red so you can relate to what you have written. This is the other part. All right, when okay. Now let us see what you are doing here. Now we have said that this is not monotonic. Okay. So what? So if it is not monotonic, so let this. So here, all of these are same. As you can see, all of these are same. Only difference. So this one is bigger. All right. But over here, because it is not monotonic, since it is not monotonic, okay, it is not monotonic. Had it been monotonic, even because this is bigger than this, so this one should have been bigger than this, but it is not monotonic. So it will have means at least a pair of rows will violate monotonicity. At least a pair of rows will violate monotonicity. This is very important. at least a pair of rows will violate. Not all rows, all rows don't have to violate, but at least a pair of rows will violate. All pairs don't have to violate. Alright. So now you have this situation, right? So now so these two you already have from here. Okay. This you already have from here, right? And this you get from here, right? And oh, sorry, sorry. I just made a mistake. Let us just see. Not, yeah, you don't do that. This is your P. This is your P. This is your variable. Alright. And all of the remaining ones you just tie up together. Alright. The remaining ones you just tie up together. So whatever be the value, it doesn't matter. You just keep them tied up together. So what you're doing is, so you have got F3. Alright. So this one has a number of inputs here. Alright. So one of these inputs is xk. Sorry. One of these inputs is xk. And all the other inputs you just tie together. They just should have the same value. And this value is either true or false. This value is either true or false. So the requisite true and false value you get. So if it is true, if it is false, you get it from F2 star. If it is true, you get it from F1 star. Alright. So whether it is, so how will you know whether it is true or false?
It should be opposite, right?
Sorry?
So it should be opposite. False we get from F.
Yeah, that's true. That is true. Yeah, false comes from F1, true comes from F2, right? So now the question is, how do you decide whether to connect it to true or false? How do you decide? Yeah, how will you decide?
Sir, depending on value of xk.
No, xk is your variable. This whole thing is you could say is so this is the input. I've just kept z output, but you just have to set z to some constant value. So what is that constant value? Should it be t or f? How will you decide? how do you decide whether it should be T or F?
Sir, if xk is f, then z should be f and vice
No, no,
versa.
no. No, no, no. You look at this. This is performing the inversion. This is P. This is P. Xk is only P. Xk
Okay, sir.
is P. Alright. Xk is P. So this is F3 dash P. Alright. So how do you decide the value of Z? See, the answer to that is actually you are probably just you have missed it a little. See, look at this, at least a pair of rows. So just let me re-emphasize this. So you basically got to look at the truth table. You got to look at the truth table. Such a pair of rows should exist, right? So you got to look at the truth table and see whether, you know, for those two rows, whether it is Z is 0 or Z is true or false. You got to look at the truth table. All right. So this comes from a truth table. Because in the truth table of F3, there must be at least a pair of rows which will violate the monotonicity. So you look at this pair of rows and see what you have, whether it is true or false. Okay. So this comes from a truth table. Is that okay now?
Yes, sir.
Yeah? So you have got your inverter, right? This is your inverter. Because
Sir,
when
but
it's
how?
false, the output is
How?
true. When the input is true, the output is false. So this is your inverter.
Sir, how
Okay.
can we conclude that the exact form of these rows, like it will be of this form only, with all z's and only one position differing at a false and true?
Yeah. Because F is non-monotonic. That is because F is non-monotonic. So if it is not monotonic, it has to satisfy this condition because if it doesn't satisfy this condition, it has to be monotonic. You understand this? If it doesn't satisfy this condition, it has to be monotonic. So if it is not monotonic, such a pair of rows must exist. Okay. That is the point. So now you have your inverter. All right. So now you know that using F1, F2 and F3, either you get the inverter the easy way or you might have to work a little more to get it this way. All right. But you can get it. So now the next thing is defining. So you need to define T and F. Now this might seem a bit counterintuitive to you, but T and F are, so now look at this part. So you need to set this to either true or false. So in the previous case, what you found is that if you have to come this far, then you get T and F from here itself. All right. So we are not actually redoing it in that sense. I mean, this is, so if you have got your inverter, let us say the hard way, then you actually need to, then you don't need to define T and F because you have already got T and F here. But if you have got it the easy way, then you don't have T and F both. or you may not have. So, so in that case, you you will have to create TNF somehow. So let us see how that can be done. So for that, let us look at F5. Okay, so F5 is not self-complementing. So if it is not self-complementing, obviously it will have such a pair of rows, right? Because you know that it will have a pair of rows whereby it is um, it gives the same output. Okay, it gives the same output. Okay, so this is a constant value, right? This is a constant value. It's a constant value, which is constant, which is either true or false. All right, it's a constant value. So you have got either true or false. So how do you know whether it is true or false? Of course, you have to look at your truth table. You got to look at the truth table of F5, and similarly the inputs. Okay, so that means, so what inputs are you going to provide here? The inputs, you are going to get either true or false. Okay, so you got to see, so whatever input you provide here, it should be the complement of that. Okay, and you already know how to you have already got the complement. So suppose, so whatever input you have here, you have to provide the complement of that here. So I'm just saying, suppose your let us consider F5 here. Okay, let us consider F5 here. This is, say, the truth table of F5. Oh, what am I doing? This is the truth table of F5. All right. I'm just taking, some sample rows. So suppose you have in your row, it is like this: T, F, F. All right. And let us say the output is T. So you have taken the complement of that, right? You have taken F, T, T. All right. So it is not self-complementing. So long as it is TFF, or for that matter, if it is it is not self-complementing. So if you consider the complement of this, so what you are going to do is, how will you wear it up? You will provide, say, any arbitrary value. Okay, so this is sorry. So here you got to provide. So let us look at this gate for F5. All right. here you got to provide, this is F5. Alright, this is the gate for F5. Alright, now, so you are going to provide some value here, and over here you are going to provide the complement here and here. Alright, so this is TFF. So, or FTT, either way, whether it is TFF or FTT. So here, if you apply, if you apply, so this is your input. So if Z takes the value T, then you are working with this row, and if Z takes the value F, you are working with this row. All right. You are working with this row. So it will be either TFF or FTT. You get it? You can see that here, right? And the output is always T. So it doesn't matter. It doesn't matter what input you give here. It doesn't depend on this input. Irrespective of whether it is true or false, you get this. Now this inverter you already have at your disposal. You have constructed it before. And you have got, say, T. So you can construct the other output. This is F. All right. So here you have T, and here you have F. So you understand how you can construct T and F from using F5, and you are using this. So for this, you know that you have already used F1, F2, and F3. All right. So what you are doing is, so this whole thing, when encapsulated, this is your F5 dash. All right. You're constructing this by this F5 dash. So you understand how to construct T and F using these gates. Is that okay? Yes?
Yes, sir.
All right. So you have come this far. One more step. Where is that? This is a bit tricky. Okay. So now we'll define a two-place function GP with an odd number of t's. All right. So now we'll consider F4. So far we have considered F1, F2, F3, and F5. So now we'll consider F4. All right. So what is F4? F4 is a function that is not counting, right? F4 is not in C. All right, F4 is not in C. Okay, so it is not counting. So if it is not counting, then what can you say? Then there must be some inputs for which it doesn't exhibit the counting behavior, isn't it? If it exhibits counting behavior for all inputs, then you can't say that it is not counting. So if it is not counting, it must exhibit, a violation of the counting behavior for some variables, and that is exactly what he is showing here. That means, what is the so we are saying that for you have some input here. This is some input, and if you look at this input, this one, so it is changing. So you have changed this. You have changed the value of this. So you must have two inputs which differ in only one place. And because it has to violate the counting behavior, so these two, the function will have the same value for both these inputs. Is that all right? Yes? Is that okay?
Excuse me, sir.
Yeah.
Sir, how will I know that that particular position is not a dummy position?
Exactly. I'm coming to that. But this much, what I have said this part, have you, are you agreeable with that? I'll answer your question, but what I've said so far, are you okay with that?
No,
Yeah?
sir, I want to say that if this, by changing only one position, if the value of the function remains the same, how can we conclude that the function is not counting? It may be that the position is a dummy
That is
position.
the next thing. That is the next thing we'll show. But you
Okay.
agree that if it is not counting, you must have such a pair of inputs. That it must have, right?
Okay. So here only the non-dummy positions are included.
No, I'm coming to that. So actually the question that you have asked, that is the next question we'll answer. So you're on the right track. We should have such an input, but you got to ensure that this position is not dummy, right?
Okay, sir. Then it is fine.
So that is exactly what we are doing. So if this position is not a dummy position, then there must be another pair of inputs. Where another set of inputs where you have a change in this position, and the result is different. So you got to have another pair of rows to show that this position is not a dummy position. All right. So you need to satisfy both these requirements. First of all, that you must have a pair of, so basically you got to have a pair of inputs which differ in a non-dummy position to give the same output. But to be sure that this is a non-dummy position, so you must have a pair of inputs where the valuation of the function is different, to be sure that this is not a dummy position, right? So now that is exactly what I've done. So I've just represented these 4 rows. This is just what I've represented. Okay. So up to here, are you okay? I've got this 4 rows over here. All right. And
Yes, sir.
for this one, the valuation is some value. I'm calling that Z1. Actually, I have written that here, but I'm just writing it close by. They'll have the same value, and for this, the value will be different. All right. The value will be different. So that's exactly what I've written. So this will be not Z2. All right. This will be not Z2. Okay. Now, let us look at some possibilities. You look at this. So let us look at the possible, relationship between uj and vj, means any column here, apart from this column, apart from this ui. So that is I not equal to j. Okay, just consider columns uj and vj. Okay. So it is possible that uj and vj are same and equal to true. So this is one condition. You have got four conditions. uj can be equal to vj and both of this can be true. This is one condition. So that's what I've written. All of this can be true. uj can be equal to vj and it can be false. All right. Both of this could be equal, and when they're equal, they could be either true or they could be false. Or they could be different, and when they're different, uj could be false, vj could be true. All right. And then you have the other possibility, they're different and uj is true and vj is false. All right. So what we can, and xi, we just say that xi is q. So we have a two value function, two place function. All right. So let us call this q, and and if they take on the same value, then we don't have a problem. We just supply this true or false, because we already have this true or false. We have already constructed this. All right. So if it is true or false, we can supply this value directly. No issues. All right. But if they differ, then that is a variable, right? So let us just say that if vj is true, we'll call that p. All right. This is, and because these are different, so this is vj is true. And of course, if vj is true, then uj will be false. All right. And the other possibility is that this is vj is false, uj is true. All right. So in this case, we allow this vj to be called p. All right. If vj is p, then of course uj is, as you can see in this case, uj is not p always. All right. So we can have it this way. So this gives us. So if we just enumerate this possibility, this table which you see here, this table, it is just an enumeration of these possibilities. So that is what I have done. I have just enumerated these possibilities. All right. So by enumerating these possibilities, I have got this 8 functions. So these are the possible values of p and q. All right. These are the possible values of p and q, and you have got this condition. This is one condition, and this is the second condition. All right. So accordingly, I've got 8 functions. Basically, if you look at this, in all of these, what you see is that 3 of these are same, 1 is different, right? So here also, if you see, always you have 3 of them same. All right. 3 of them same and 1 different. 3 of them are same and 1 is different. Same here. You have got 3 of them same, 1 different. Oh, sorry. 3 of them same, 1 different. All right. So these are I've just enumerated the various possibilities that you can have from this. So by enumerating these possibilities, you get 8 functions: G1, G2, G3, G5, G4, G5, G8. And if you look at the truth tables, if you look at this, you find that this one is OR, this one is reverse implication. Reverse implication means P is implied by Q. This one is the opposite of that. This is P is not implied by Q. So you could write it like this if you like. This is NOR. This is NOR. So this is forward implication. This is P implies Q. This is NAND. This is and this is not P implies Q. Alright. So what you find is that, so some of these you can use directly. So this one and this one you can use directly, or you can use in conjunction with NOT. Alright, or you can use in conjunction with NOT. This also you can use in conjunction with NOT, and so on. Implication can be used in conjunction with NOT, and this reverse implication, actually this implication is like OR only. This implication is like OR only. P implies Q. This is not P or Q. All right. So if you have an implication gate, so if you put an inverter here, what do you get? This is simply an OR gate. All right. This is simply an OR gate. So that is what it is. So using implication, essentially you can get an OR gate, and of course once you have got OR, and say NOT, then this is functionally complete. All right. So implication NOT is functionally complete. For that matter, if you have reverse implication is simply you have this, you put the NOT on the other side. So if you have reverse implication, you just put NOT on the other side. To get OR again. So both of these are OR. Okay. And so that is it. This is so if it is not, then you just got to put another. Actually, if it is if it is not reverse implication, then the gate you get as a result of this, what gate is this? This is a NOR gate. All right, this is a NOR gate. So similarly, with this also you can get a NOR gate. With this also you can get a NOR gate. So that is basically what we have, what you see.
Sir, you are on mute.
Yeah, okay. So, yeah, so that is our, our treatment on this functional completeness. So what I've seen is that so long as you have this, uh, 5 functions, they don't have to be distinct. Some of this, for example, you have seen the NAND function. The NAND function is, it belongs to all of those. I mean, or rather, it doesn't belong to any of those classes. So by itself, it is enough. You don't, as you have seen, by itself it is functionally complete. You don't need anything else. Yeah. Um, yeah. So that is the treatment of functional completeness. And so let us come to the lab assignment. Lab assignment I am yet to write down, but I'll just tell you what it is going to be. So you will be given, some functions f1, f2, f3, f4, and f5, and using those functions, you just have to follow this, this procedure and complete and construct a functionally complete set of, functions. That's all. That is the assignment. So I'll be writing it down and putting it up, but that will be the assignment. So any questions here? Yeah. Hello. Hello.
Hello.
Yeah. So that is all. So do you have any questions? All right. So if you don't have any questions, then we can close now. All right.
So CRM, they are apparently they are having some
Yeah, you have been muted. You please unmute.
so we have some queries regarding the evaluations. So should we forward them to the
That
TS
is
or?
going on. So that I think let us just give the TS some time. Let them sort out. After that, also if queries remain, then we'll take those up.
So I mean, you tell us what your queries are. Maybe you can mail or something.
No,
So
they
Kaushal,
are posted. They have posted the queries,
they are
and I
posted
think,
also exactly.
yeah, I think many
Hmm.
of those issues have been resolved. Some are still pending. So we will just give the TS a little more time. Let them sort out the issues. If something still remains, then we'll take a look.
Okay.
Yeah. All right.
Okay.
Okay
Then I
then.
think good night. Uh-huh.
All right. Okay then. We can stop here. Yeah.
Sir,
Yeah.
actually, ma'am has said that all the posted queries have been resolved by her, but we still have some doubts.
Yeah, okay, I'll talk to her. I'll talk to her. So I think she will know which queries are still pending. So let me talk to her. Then we'll discuss with you. I mean, we'll just tell you to put your queries, the unresolved queries that you still have. We'll discuss those. All right. So let me first discuss with her. I have not yet discussed with her about this. Yeah.
Sir, could you please upload today's slides?
Already uploaded. It is the same set. SCLD BA. With some more slides. So I've already uploaded these slides. Yeah.
Okay, thank you, sir.
Yeah. All right. Okay. So anything else? All right. Then I'm closing. Yeah.
Hello, sir.